Welcome to our channel. Today we're diving into one of the most exciting fields in modern astronomy, the detection of exoplanets. These mysterious worlds orbit stars outside our solar system, and their discovery has transformed our understanding of the universe. But why is this topic so significant, and what makes the search for exoplanets so fascinating? First, let's clarify what we mean by exoplanets. An exoplanet, or extrasolar planet, is a planet that exists outside our solar system. Unlike the 8 planets that orbit our sun, exoplanets orbit other stars, ranging from sun-like stars to distant faint red dwarfs. These planets can be wildly different from what we know in our solar system. Some might be gas giants like Jupiter, others could be rocky and Earth-like, and some may have extreme environments unlike anything we've ever seen. The first confirmed discovery of an exoplanet was made in 1992 by astronomers Alexander Wolfson and Dale Frail. They identified 2 planets orbiting a pulsar, a type of neutron star, using radio telescopes. This groundbreaking discovery opened the floodgates for further research, leading to the identification of thousands of exoplanets in the decades that followed. It demonstrated that planets could form in a variety of environments, even around the remnants of exploded stars. Studying exoplanets is crucial for several reasons. It helps us understand the formation and evolution of planetary systems, including our own. By comparing different planetary systems, we gain insights into the diversity of planets in the galaxy and the processes that shape them. Moreover, the search for exoplanets is intrinsically linked to the quest for extraterrestrial life. Identifying planets in the habitable zone, where conditions might be right for liquid water and potentially life, brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Stay tuned as we explore the fascinating methods astronomers use to detect these distant worlds and what these discoveries mean for the future of space exploration. The transit method, one of the most successful techniques astronomers use to detect exoplanets, is the transit method. This method has revolutionized our understanding of planetary systems beyond our own, and has led to the discovery of thousands of exoplanets. But what exactly is the transit method, and how does it work? The transit method involves monitoring the brightness of a star over time. When a planet passes or transits in front of its host star from our point of view, it causes a slight but detectable dip in the star's brightness. This dip occurs because the planet blocks a small fraction of the star's light as it moves across its face. By carefully measuring these periodic dips in brightness, astronomers can infer the presence of an exoplanet. Imagine looking at a light bulb. If a tiny speck like a dust particle passes in front of it, the light appears to dim just a bit. Similarly, when a planet crosses its star, the light we receive from that star dims slightly. This dimming is known as a transit. By analyzing the timing, depth, and duration of these transits, astronomers can gather a wealth of information about the exoplanet. First, the size of the planet can be estimated based on how much the star's light dims. A larger planet will block more light and cause a more significant dip in brightness. Second, the period between transits indicates the planet's orbital period, or the time it takes to complete one orbit around the star. This data helps determine the planet's distance from its star and its orbital characteristics. Moreover, if the transit method is combined with other techniques, such as the radial velocity method, astronomers can determine the planet's mass. Knowing both the size and mass of the planet allows scientists to calculate its density, which provides clues about its composition, whether it is a rocky planet like Earth or a gas giant like Jupiter. One of the most remarkable aspects of the transit method is its ability to provide insights into an exoplanet's atmosphere. During a transit, a small fraction of the starlight passes through the planet's atmosphere before reaching us. By analyzing this light, astronomers can identify the chemical composition of the atmosphere, detecting gases such as hydrogen, helium, water vapor, methane, and even potential signs of life. However, the transit method comes with its challenges. For one, it requires extremely precise instruments capable of detecting minute changes in a star's brightness. Even a giant planet like Jupiter causes only a small dip in brightness, roughly 1%. Detecting Earth-sized planets, which cause even smaller dips, requires highly sensitive equipment and meticulous data analysis. Another challenge is that a planet's orbit must be aligned just right with our line of sight. If the orbit is tilted too much, the planet won't pass in front of the star from our perspective, and no transit will be observed. This means the transit method can only detect a fraction of the planets that exist, those with favorable orbital alignments. Despite these challenges, the transit method has been incredibly successful, thanks in large part to dedicated space missions. The Kepler Space Telescope, launched in 2009, was designed specifically to find Earth-sized exoplanets using the transit method. Kepler observed over 150,000 stars and discovered more than 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. Its successor, the Transiting Exoplanet Survey Satellite, TESS, launched in 2018, continues this legacy. TESS scans almost the entire sky, focusing on the brightest stars, and has already identified numerous new exoplanets. These missions have expanded our knowledge of the universe, revealing an astonishing diversity of planets. From hot Jupiters orbiting close to their stars to potentially habitable Earth-sized planets in the habitable zone, the transit method has shown us just how varied and fascinating planetary systems can be. In summary, the transit method is a powerful tool for detecting and studying exoplanets. By monitoring the tiny dips in a star's brightness caused by transiting planets, astronomers can learn about the size, orbit, and even the atmospheric composition of these distant worlds. The challenges are significant, but the rewards, greater understanding of the universe and the potential discovery of habitable planets, make it all worthwhile. The radial velocity method. Now that we've explored the transit method, let's delve into another powerful technique used by astronomers to detect exoplanets. The radial velocity method, also known as the Doppler method. This technique has been instrumental in discovering some of the first exoplanets and continues to be a crucial tool in our search for worlds beyond our solar system. The radial velocity method works by detecting the subtle wobble of a star caused by the gravitational pull of an orbiting planet. When a planet orbits a star, it exerts a gravitational force on the star, causing the star to move in a small orbit around the common center of mass of the star-planet system. This movement causes changes in the star's velocity relative to Earth, which we can measure using the Doppler effect. The Doppler effect is the change in frequency or wavelength of light from a source that is moving relative to an observer. In the context of exoplanet detection, when the star moves toward us, its light is slightly blue-shifted, meaning its wavelengths are compressed. Conversely, when the star moves away from us, its light is red-shifted, meaning its wavelengths are stretched. By precisely measuring these shifts in the star's light spectrum, astronomers can determine the star's radial velocity, its speed along our line of sight. To measure these shifts, astronomers use highly sensitive spectrographs attached to telescopes. These instruments can detect changes in the star's light as small as a few meters per second. By analyzing the pattern and amplitude of these velocity changes over time, astronomers can infer the presence of an orbiting planet. The period of the velocity changes reveals the orbital period of the planet, while the amplitude indicates the planet's mass and the size of its orbit. One of the significant advantages of the radial velocity method is its ability to determine the minimum mass of an exoplanet. However, without knowing the exact inclination of the planet's orbit, we can't determine the precise mass. Instead, we get a minimum mass estimate, assuming the planet's orbit is edge-on. If the orbit is tilted, the actual mass could be higher. The radial velocity method excels at detecting larger planets that are close to their stars, such as hot Jupiters. These massive planets exert a stronger gravitational pull on their stars, causing more significant wobbles that are easier to detect. This method was pivotal in the discovery of 51 Pegasi b, the first exoplanet found orbiting a Sun-like star in 1995. This hot Jupiter orbits its star in just 4 days and has a minimum mass about half that of Jupiter. This groundbreaking discovery by Michel Mayor and Didier Queloz earned them the Nobel Prize in Physics in 2019. Despite its success, the radial velocity method faces several challenges. Detecting the tiny wobbles caused by smaller Earth-like planets requires extremely sensitive instruments and stable observing conditions. Stellar activity, such as star spots or flares, can also mimic the signals of an orbiting planet, leading to false detections. Moreover, the method is less effective for detecting planets in wide orbits, as their gravitational influence on the star is weaker and takes longer to observe. Notable discoveries using the radial velocity method include not only hot Jupiters, but also multi-planet systems and planets in the habitable zones of their stars. One such example is Gliese 581. A red dwarf star with a system of planets, including Gliese 581d, which lies within the star's habitable zone. This discovery sparked significant interest in the potential for habitable exoplanets. Advancements in technology continue to improve the radial velocity method. Instruments like the HARPS, High-Accuracy Radial Velocity Planet Searcher, spectrograph have pushed the limits of precision, allowing astronomers to detect smaller and more distant planets. Future missions and telescopes, such as the Extremely Large Telescope, ELT, promise even greater sensitivity and the potential to discover Earth-like planets around Sun-like stars. In summary, the radial velocity method is a cornerstone of exoplanet detection. By measuring the tiny wobbles of stars caused by orbiting planets, astronomers can determine the presence, mass, and orbit of these distant worlds. While it has its challenges, the method has yielded significant discoveries and continues to be a vital tool in our quest to understand the universe and find potentially habitable planets beyond our solar system. The direct imaging method. Next, let's explore the direct imaging method, one of the most visually striking techniques used to detect exoplanets. Unlike other methods that infer the presence of exoplanets indirectly, direct imaging aims to capture actual images of these distant worlds. Although it sounds straightforward, it's a highly challenging and sophisticated process. The direct imaging method involves taking pictures of exoplanets by directly observing the light they reflect or emit. This approach allows astronomers to study the physical and atmospheric properties of exoplanets in detail. However, the primary challenge is that stars are much brighter than their planets. For example, a star like the Sun can be billions of times brighter than the reflected light from an orbiting planet. This extreme contrast makes it difficult to distinguish the faint light of a planet from the overwhelming glare of its host star. To overcome this challenge, astronomers use instruments like coronagraphs and star shades. A coronagraph is an optical device inside a telescope that blocks the light from a star, allowing the dimmer light from surrounding objects, such as planets, to be seen. Star shades, on the other hand, are large, flower-shaped structures positioned in space to block a star's light before it enters the telescope. These technologies significantly reduce the star's glare and make it possible to image nearby exoplanets. Direct imaging is particularly effective for studying large planets that are far from their stars. These planets reflect more light and are less affected by the star's brightness. Additionally, planets located at greater distances from their stars are easier to separate visually from the star's light. This method is also beneficial for studying young planetary systems, where planets may still be warm and emit more infrared light, making them easier to detect. Despite its advantages, the direct imaging method faces several challenges. The primary difficulty is the extreme contrast in brightness between stars and their planets. Achieving the necessary precision to block out the star's light while capturing the faint light of the planet requires advanced technology and meticulous calibration. Furthermore, Earth's atmosphere can distort images taken from ground-based telescopes, necessitating the use of adaptive optics or space-based observatories to achieve the required clarity. Nevertheless, there have been several successful instances of direct imaging of exoplanets. One notable example is the HR 8799 system, where astronomers have directly imaged multiple planets orbiting the star. These gas giant planets are located far from their host star, making them ideal candidates for direct imaging. Another significant achievement is the imaging of Beta Pictoris b, a gas giant orbiting the young star Beta Pictoris. Observations of Beta Pictoris b have provided valuable insights into the planet's atmosphere and orbital dynamics. The development of next-generation telescopes promises to enhance the capabilities of the direct imaging method. The James Webb Space Telescope, JWST, now operational, has advanced coronagraphs designed to directly image exoplanets and study their atmospheres. Similarly, future missions like the Nancy Grace Roman Space Telescope will feature star shades to block starlight and enable the direct imaging of exoplanets. In summary, the direct imaging method offers a unique and powerful way to study exoplanets by capturing their actual images. While it faces significant technical challenges, advancements in telescope technology and innovative instruments like coronagraphs and starshades are paving the way for more successful direct imaging endeavors. This method holds great promise for uncovering the physical characteristics and atmospheric compositions of distant worlds, bringing us closer to understanding the diverse nature of planetary systems in our galaxy. The gravitational microlensing method. Another fascinating technique astronomers use to detect exoplanets is the gravitational microlensing method. This method takes advantage of the gravitational lensing effect predicted by Einstein's general theory of relativity. While it might sound complex, the basic principle is straightforward and incredibly powerful. Gravitational microlensing occurs when a massive object, such as a star or planet, passes in front of a more distant star. The gravity of the foreground object acts like a lens, bending and magnifying the light from the background star. This effect causes the background star to appear temporarily brighter. If a planet is orbiting the foreground star, its gravitational influence can create a noticeable blip or additional brightening in the light curve of the background star. Imagine looking at a distant streetlight through a magnifying glass. As you move the magnifying glass, the light bends and changes in brightness. Similarly, when a planet passes in front of a distant star, it creates a detectable change in the star's brightness. By analyzing these changes, astronomers can infer the presence of an exoplanet. The beauty of gravitational microlensing is that it can detect planets that are otherwise difficult to find using other methods. It is particularly sensitive to planets located far from their host stars, and even to free-floating planets that are not bound to any star. This method can also detect planets in the habitable zone, where conditions might be right for liquid water. However, gravitational microlensing comes with its own set of challenges. One major challenge is the rarity and unpredictability of microlensing events. These events occur only when the alignment between the foreground and background stars is just right, which happens infrequently and unpredictably. Continuous monitoring of millions of stars is required to catch these fleeting events. Despite these challenges, the gravitational microlensing method has led to some unique and groundbreaking discoveries. One notable example is the discovery of OGL 2005 BLG 392LB, a planet located about 21,500 light-years away. This planet, with a mass about 5 times that of Earth, was found using the Optical Gravitational Lensing Experiment, OGL, and is one of the most distant exoplanets discovered. Another exciting discovery is the detection of free-floating planets, which are not bound to any star and roam the galaxy independently. These planets are challenging to detect with other methods, but microlensing has provided evidence of their existence. The astrometry method. Moving on to another technique, let's discuss the astrometry method, one of the oldest methods used to search for exoplanets. Astrometry involves precisely measuring a star's position in the sky over time to detect the slight wobble caused by the gravitational influence of an orbiting planet. When a planet orbits a star, the star doesn't remain stationary. It moves in a small orbit around the center of mass of the star-planet system. By tracking the star's position relative to distant background stars, astronomers can detect these tiny movements. This method can reveal the presence of planets and provide details about their orbits. Astrometry requires extremely precise measurements because the changes in a star's position caused by an orbiting planet are minuscule. This precision is challenging due to the vast distances involved and the need to observe the star's position over long periods. Additionally, this method is more effective for detecting large planets with significant gravitational effects on their stars. Despite these challenges, astrometry holds promise for future discoveries. It can detect planets in a wide range of orbits, including those far from their stars, which are often missed by other methods. With advancements in technology and more precise instruments, astrometry could become a crucial tool in the search for exoplanets. One of the most notable missions utilizing astrometry is the European Space Agency's Gaia mission. Launched in 2013, Gaia aims to create a precise three-dimensional map of our galaxy. By tracking the positions and movements of over 1 billion stars, Gaia is expected to discover thousands of new exoplanets and provide valuable data on their characteristics. Combining methods for confirmation. Often, astronomers use multiple methods to confirm the presence of an exoplanet. This multi-method approach helps ensure the accuracy of the findings and provides a more comprehensive understanding of the planet's characteristics. For example, a planet detected by the transit method can be further studied using the radial velocity method. The transit method provides information about the planet's size and orbit, while the radial velocity method can determine its mass. By combining these methods, astronomers can calculate the planet's density and infer its composition, whether it is rocky like Earth or gaseous like Jupiter. Combining methods also helps eliminate false positives. For instance, stellar activity or binary star systems can sometimes mimic the signals of an orbiting planet. Using multiple detection techniques helps cross-verify the data and confirm the planet's existence. This integrated approach has been instrumental in many significant discoveries. For example, the TRAPPIST-1 system, which has 7 Earth-sized planets, was discovered using a combination of transit and radial velocity methods. This detailed information has provided valuable insights into the potential habitability of these planets and their overall system architecture. Notable exoplanet discoveries. Let's highlight some of the most significant exoplanet discoveries that have shaped our understanding of planetary systems. One of the most notable is the TRAPPIST-1 system, which consists of 7 Earth-sized planets orbiting a cool dwarf star. Discovered using the transit method, this system has intrigued scientists with its potential for habitability. Another remarkable discovery is Proxima Centauri b, an Earth-sized planet orbiting the closest star to the Sun, Proxima Centauri. Detected using the radial velocity method, this planet lies within the star's habitable zone, raising exciting possibilities for the existence of liquid water and life. Kepler 186f, discovered by the Kepler Space Telescope, is another significant find. This Earth-sized planet orbits within the habitable zone of its star, making it one of the best candidates for studying potentially habitable environments. The discovery of free-floating planets through gravitational microlensing has also been groundbreaking. These rogue planets, not bound to any star, challenge our understanding of planetary formation and dynamics. These discoveries have not only expanded our knowledge of the diversity and complexity of planetary systems, but have also fueled the search for habitable worlds beyond our solar system. The future of exoplanet research. The future of exoplanet research is incredibly exciting, with several upcoming missions and technological advancements poised to revolutionize the field. One of the most anticipated projects is the James Webb Space Telescope, JWST, set to launch soon. JWST will have advanced instruments capable of directly imaging exoplanets and analyzing their atmospheres in unprecedented detail. Another promising mission is the European Space Agency's PLATO, Planetary Transits and Oscillations of Stars, which aims to discover and characterize Earth-sized exoplanets in the habitable zones of sun-like stars. PLATO will use a combination of transit and astroseismology methods to study planetary systems and their host stars. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the world's largest optical and infrared telescope. Its immense size and cutting-edge technology will enable it to detect and characterize smaller exoplanets, including those similar in size to Earth, and study their atmospheres for signs of habitability. In addition to these missions, advances in artificial intelligence and machine learning are enhancing our ability to analyze vast amounts of data from exoplanet surveys. These technologies will help identify subtle signals that may indicate the presence of new planets. The future also holds the potential for innovative methods, such as star shades and more advanced coronagraphs, which will improve our ability to directly image exoplanets and study their properties. These advancements will bring us closer to answering profound questions about the potential for life elsewhere in the universe and the diversity of planetary systems. How you can get involved. You might be wondering how you can get involved in the exciting field of exoplanet research. There are several ways for enthusiasts and citizen scientists to contribute to this fascinating area of study. One way is through citizen science projects like those hosted on Zooniverse. Projects such as Planet Hunters and Exoplanet Explorers allow you to analyze real data from telescopes and help identify potential exoplanet candidates. Your contributions can lead to actual discoveries and further our understanding of the universe. Another way to get involved is by staying informed and supporting space research initiatives. Follow the latest news and discoveries in astronomy. Participate in public lectures and events, and consider joining local astronomy clubs or societies. These communities often offer opportunities to learn more about exoplanets and contribute to outreach and education efforts. You can also support organizations that fund and conduct exoplanet research, such as NASA, the European Space Agency, and various astronomical institutions. Your support helps drive the development of new technologies and missions that will continue to expand our knowledge of distant worlds. In conclusion, the detection of exoplanets is a complex and fascinating process that has expanded our understanding of the universe. Each method, transit, radial velocity, direct imaging, gravitational microlensing, and astrometry, contributes uniquely to our knowledge. The challenges are significant, but the rewards, greater understanding of the universe and the potential discovery of habitable planets, make it all worthwhile. Thank you for joining us on this journey through the cosmos. If you enjoyed this video, don't forget to like, share, and subscribe for more exciting content about the wonders of the universe. Until next time, keep looking up and stay curious. See you in our next video.